Hello everyone, welcome back. I am Alok Kumar, and today it is going to be the second lecture in the two-lecture series on the trigonometric equations. So let me now share my screen with you all and start the lecture. Okay, so yesterday already I had covered different models of equations, and whatever is left, we'll cover today. So to begin with, we start one example which asks you to find all k belonging to R such that the equation, so k belongs to R such that the equation sine of x plus cos of k plus x plus cos of k minus x equal to 2, this has real solutions. I can also phrase this as, instead of this one, I can write has a real solution. That is same, the question does not change, has a real solution, or has at least one real solution, or I say that has some real solution. So all these expressions mean the same thing. So let me repeat the question. It says that find all k is a parameter. So find all k that belongs to R such that the equation sine of x plus cos of k plus x plus cos of k minus x equal to 2 has real solutions, or has a real solution, or has at least one real solution, or has some real solution. Now this is a beautiful question combining parameter also and trigonometric functions. So what we do, that first we look up this term cos k plus x, that invites cos of a plus b plus cos of a minus b. So we can pair them off, and I get from sum to product. So I'll get cos a plus cos b, and so it is 2 times you will get cos of a and times cos of x. So either you are using cos c plus cos d, or you can simply use cos of a plus b plus cos of a minus b. They are both same thing. Now if this is there, then we get 2. Now cos k is the variable, and of course x also, but x is the variable thing and cos k is the parameter thing. So let me write it as sin x plus 2 cos k and times cos x equal to 2. So we see that this is of the form a sin x plus b cos x equal to c. And you don't want to find x, rather your interest is that what these k's must be, means what are the range of k, or what is the set of values of k such that the equation, this equation has got at least one real solution, means it has some x element of R that satisfies it. So we are back to this one. We know that for this equation to have solution x element of R, it is both necessary and sufficient, that is if and only if, or we say it is both necessary and sufficient, that's important word. So it's both necessary and sufficient that modulus of c less than equal to square root of a squared plus b squared. To quickly walk you through the proof, it is simply we will divide by a over root a squared plus b squared and such things, and you will get here c upon root a squared plus b squared. And you know that this thing over the left side can be written as either sine of x plus theta or cos of x plus theta. And so this thing, this modulus must be less than equal to 1, and so you will get this one. So to hammer the point again, that a sin x plus b cos x equal to c has at least one real solution if and only if modulus of c less than or equal to root of a squared plus b squared. This is what makes it work. Now we are good. So we want this to have one solution, at least one solution. So I will say that one is this 1 square plus 4 cos square k, that is your root square b squared. So you know that this root, and then 4, this 4 must be less than equal to this. That's what we did, that we said that mod c, so mod c actually it is 2, so I'll write here 2. So this is 2 less than equal to this one. I can square it because they are equivalent to get 1 plus 4 cos square k. So I'll get 3 less than or equal to 4 cos square k, giving you cos square k greater than or equal to 3 over 4. Now a piece of advice: if you are dealing with this cos k, we have two choices: either deal with cos or go to sine. Here sine is much better because you get less than or equal to. So I can write 1 minus sine square k greater than equal to 3 over 4, and so sine square k less than or equal to 1 over 4. Now that's nice because we will get here that minus 1 over 2 less than equal to sine of k less than equal to 1 over 2. And we know that when this is the case, then actually this half becomes pi by 6, corresponds to this one. So we know that k less than equal to n pi plus pi over 6, and this is less than equal to n pi minus pi over 6. And so we know that this is your solution for all k, and n element of G, that is n is 0, plus minus 1, plus minus 2, and all those numbers. This is an advantage in using sine square k. We can write the result in symmetrical form. Cos would have invited more work. Okay. As a second example, again inequalities and combinations of even quadratic. So this says that find all alpha that belongs to R. They are all question based on parameter, which of course gives much trouble to students. So I'm trying to take the mystery out of it. So find all alpha element of R belong to R such that sine to the power 4x plus cos to the power 4x plus sine 2x and plus alpha equal to 0 has a real solution, real root. Same thing, real solutions or real solutions. I can use plural also. So now this solution idea, I'll do it by say 3 methods. Just look at it very carefully and try to find which is more efficient. Of course, I will give my judgment and I will be comparing that which is more efficient and which cases. Now, the first thought that comes to our mind is that these powers are too big, sine 4 and cos 4. So I can write them at sine to the power 4x plus cos to the power 4x as sine square x plus cos square x whole squared and minus twice sine square x cos square x. This is 1, that's good enough. And this I can write as 1 over 2, and this is 4 sine square x cos square x, because that tells me that I can further write twice sine x cos x whole square, and then it is 1 minus half, and this is sine square 2x. Already we have got sine 2x here, so that gels well with it. Now our equation reduces to 1 minus half sine square 2x plus sine 2x plus alpha is 0. I can further rewrite it, little bit I can change, and I can write this as negative of sine square 2x plus 2 sine 2x in order, and plus 2 alpha and plus 2 equal to 0. I can once again change the sign. Sine square 2x minus 2 sine 2x minus 2 alpha plus 2 equal to 0 means that right now we have just got an equivalent equation. This is equivalent. So requiring that find all alpha such that this equation 1 has a real solution is equivalent to asking that this equation 2 has got a real solution. Further, 2 alpha plus 2, of course, I can put some other number. So negative of 2 alpha plus 2 total I can put as beta. These kind of things help because then I can focus on beta. There is no need to carry this one. Once I get beta, I can get alpha also by linear transformation. Now I look at it as some kind of quadratic. So I can say that this is same thing as some function, say f of t. F of t is some function that is t square minus 2t and plus beta. So this is ft function, and this is 0, you are saying quadratic. Now you are saying that find all betas, meaning find all alphas by extension. So find all betas such that this equation has now at least one root. This is important, at least one root in the interval in the interval -1 to 1, because you have assumed sine 2x equal to t. X can range all over R, but sine 2x is not allowed. You know it's only from -1 to +1. And so the equivalent problem would be that your question becomes, we are further reducing the problem. So we are saying that, okay, given a quadratic, you tell me all values of beta such that this quadratic in T has got at least one root, at least one, because at least one we are one, not both, at least one root in the interval -1, 1 as sine 2x belongs to this one. Now, so first method I will do that, suppose I write this way, that the sum of roots, you see the sum of roots, so t1 plus t2 sum of roots is 2. So if one root is not 1, if one root is 1, other also will be 1. So suppose root is not 1, then one root is less than 1 and other greater than 1. So it means the root that is greater than 1, that will work for us, because you want at least 1. So both is not required. That is 1. So it means we can say that in -1 and 1, it can never happen that it has both roots. Means it becomes that in -1, 1, you want to have exactly one real root. Mind you, it's a big improvement. You are given at least 1. Now at least 1 cases are dealt by both or exactly 1. Union of 2 cases, both or exactly 1. But here both roots cannot be in -1 to 1. That we can see, because if one root is 1, then other root has to be less than 1 if it is not 1, because sum is 2. It means that it is enough to consider that it has got exactly one real root, not at least exactly one real root in -1, 1. And the condition for that in terms of quadratic is that f minus 1 and f of 1, this is less than or equal to 0. Equal to 0 is achieved because you can have -1 and 1 also as a root, possibly. And the condition that it has a strictly a root between -1 and 1 is strictly, that is given by f minus 1, f1 less than 0. That is at -1 and +1, f must have different sign. If we combine this, we get these two after combining. So this is the condition for us to have that this equation in T will have at least one real root, that is exactly one real root by consideration in the interval -1, 1. So now f minus 1, now just left to calculate f -1, that is 3 minus beta, and f +1, 1, as you can see, it's -1 plus beta, so that is less than equal to 0. That is we will get, this is 3 plus beta, so we will get beta plus 3 and beta minus 1 less than equal to 0, and so I get -3 less than equal to beta less than equal to 1. But we wanted to find alpha. No problem, our thing was beta was here, beta is -2 alpha plus 2, so I'll write -3 less than equal to -2 alpha plus 2 less than equal to 1. I can turn the sign, so 3 greater than equal to 2 alpha plus 2 greater than equal to -1. That is, I can subtract 2 from each side, so that is 1 greater than equal to 2 alpha greater than equal to, this is negative of 3, and so I can divide by 2, so 1 over 2 greater than equal to alpha greater than equal to -3 over 2, and I can write in a form that -3 by 2 less than equal to alpha less than equal to 1 over 2. So I found that the set of all alphas such that the given equation, this is my answer, the boxed one. So I found the set of all alphas such that the given equation, the one original given one, has got at least a real solution is given by alpha belongs to -3 by 2 to 3 by 2. So 3 by 2 to 1 by 2. So that's my answer. Let us do by a second method, second solution. Well, second solution is like, we see this equation is linear in beta. Look at it again, linear at beta. So I can write here that negative of beta is t squared minus 2t, and remember we want t element of -1 to 1, so we want all those betas, and then we will get by extension alpha also. We want all those betas such that this equation has got at least one solution in -1 to 1. Now that's just requires that let's graph it. T square minus 2t. That's that's like this. I don't draw y-axis, not needed. So this one root is 0, other root is 2. Only x-axis is drawn. This corresponds to 1 because minus b by 2a. If you remember, this is minus b over 2a. So now 1, and you want from negative 1 to 1. So you want from negative 1 somewhere here, negative 1 to 1. So it means, let me change the color and show you that this is our interest in this one, is this one. So this is the graph, our interest is this one. We know that this function, t square minus 2t quadratic function, this has got the greatest value attained at, say, we can again call it f of t, we call it g of t this time, because if we use g of t, so we know that the greatest value is this one, g negative 1, and that happens to be 3. And the least value is g of 1, and that happens to be negative 1. So it means that if minus beta lies between these two numbers, then we are good, because then we will always get a solution in this interval minus 1 to 1. So it means the condition becomes that minus beta must belong to the range of gt, and so we will say that minus beta must belong to the interval negative 1 to 3. And so it is same thing, negative 1 less than equal to negative beta less than equal to 3. Now this is the same thing we got. If we change the sign, 1 greater than equal to beta greater than equal to negative 3, I can rewrite negative 3 less than equal to beta less than equal to 1, and just check the beta that we got last time. It was exactly the same. That is this one, negative beta. So we are here, we got for beta this one, and they are same. And so we will say that this is our solution. So solution ends. Now we can calculate alpha. Third solution. So before giving third solution, let me remark, first solution was guessing or that location of roots. So this chapter will be called location of roots in quadratic. That was all right. Second solution was not much lengthier. Why? Because in second solution we found that in fact I can solve for beta, and whenever this is possible, that you can solve for parameter. So if parameter is on one side, parameter one side, and function other side, then just find the greatest and least value of the function. This is parameter and right side, and then must make sure that parameter lies in this interval. That's all. That will be done. That is the best. So second is the better of the two. You will find is the best, in fact. The third is, of course, the routine one. Not very interesting, but still, if you don't get these two ideas, then sometime that can save the day. So here we just write plain approach that we are here t square minus 2t plus beta. So we will write that t square minus 2t plus beta equal to 0, and we want that t must belong to negative 1 to 1. So we solve for t only, that is negative of b. So that is this one, 2 plus minus root of b squared minus 4ac and upon 2. And so we got 1 plus minus root 1 minus beta. Of course, for any solution, 1 minus beta must be greater than equal to 0. Otherwise, there is no solution. And then once that is true, you will find that for beta equal to 1, you are getting t equal to 1 and 1. Beta, of course, cannot be greater than 1. And if beta is less than 1, then one of the root is 1 plus negative beta and 1 minus root 1 minus beta. So, of course, that root will not work. If beta is not 1, beta is not 1. Of course, beta has to be less than 1. So it means this will be positive. So this root exceeds 1, it won't work. So the only root that is left out is this. So it means you want this root to belong to negative 1 to 1. And so you will write that negative 1 less than equal to 1 minus root 1 minus beta less than equal to 1. First solve the right side. That is 1 minus square root of 1 minus beta less than equal to 1. That one goes off. And then you can multiply by negative and sign will turn. This is greater than equal to 0, which is anyway satisfied because it's non-negative number. So it gives you all such betas, which still makes this defined. So no such number you get here. On the left side, you get negative 1 less than equal to 1 minus square root of 1 minus beta. You can transfer this to left side, less than equal to 2. And then I can write 1 minus beta less than equal to 4. I can square. They are equivalent. And then I can write negative 3 less than equal to beta. So I'm getting beta greater than equal to negative 3. and beta less than equal to 1 here for function to be defined. Combining this and combining this, we still get -3 less than equal to beta less than equal to 1. So this has the feature of being simple, but mind you, it is irrational, and so sometimes that may be very tedious expression. And so I would recommend the approach first, because first is more general. Second, you got just lucky because beta was linear, and so you were able to write beta on one side and all variables on other side, and then second solution is also possible. This is a good example, very much instructive, so please keep in mind. So I took much trouble to explain it also. Okay, let's go on to the next one. Already we have done determinant and other things, so it makes sense now to do some question that in this language. So one question is this, that let lambda alpha belong to R. This is a J equation, and then you want to find all lambda belong to R such that the system, so the system is written in this form, such that the system lambda x plus sine alpha times y and plus cos alpha times g equal to 0, and x and plus cos alpha times y and plus sine alpha times g equal to 0. And the third equation is still remaining, negative x plus sine alpha times y and negative cos alpha times g equal to 0. So they are saying that this system of course linear equations has a non-trivial solution, So you want all those lambdas such that this system of equation has got one linear solution in, of course, one non-trivial solution in x, y, and g. Of course, lambda alpha both are parameter, but you want lambda, what lambda can be. Now this brings you to trigo also, and then matrix determinant. So first write the system as ax equal to 0. I told you previously that A is now just the coefficient matrix, that's lambda, sine of alpha, cos alpha, then 1 and cos of alpha and sine alpha, and -1 sine alpha and minus cos of alpha. That is your A. Your x, as usual, is x, y, g, the column vector, this one. And this equation, the system of three linear equations, for which matrix theory gives an elegant method, reduces to ax equal to 0. It's very brief and succinct, means that it is like just it captures the essence of all in just one catchy sentence, ax equal to 0. Okay, now you want that this should have non-trivial solution, so because it always have a trivial solution, x equal to 0, that is true. 0 0 0 is, of course, you can put it is homogeneous, so that's no brainer. So of course anybody will give you non-trivial. Now we know that it happens if and only if, one of the favorite words, if and only if. So it means it is both necessary and sufficient that this det of A should be 0. Det of A means this A matrix, det of A should be 0, because by contradiction, if det of A is not 0, means A is invertible, and then you have got A inverse Ax equal to 0, giving x equal to 0, the trivial one. So it means it is both necessary and sufficient that det of A must be 0. Then we will get non-trivial solution. So you just have to mess this 0. So that's lambda. So it's now matrices. Now we have not yet reached till this trigonometry, and -1 sine alpha and minus cos alpha equal to 0. Now I can just expand because there is no such good thing. So I can simply expand. So lambda times, and so lambda times I will get negative of cos square alpha minus negative of sine square alpha, and then plus sine alpha times negative of sine alpha plus cos alpha. Just don't make any mistakes. Cos alpha and times this is sine of alpha plus cos of alpha equal to 0. And I collect the term. This is negative alpha, negative lambda, and then this is negative sine square alpha, and then plus sine alpha cos alpha plus cos alpha sine alpha, and plus cos square alpha is 0. I am getting negative lambda and then negative sine square alpha and cos square alpha, that is cos 2 alpha, and then this is sine 2 alpha, 2 sine alpha cos alpha, sine 2 alpha is 0. So it means if you want this system to have non-trivial solution, that lambda and alpha must be bound by this relation, means lambda and alpha must obey this equation. So it means if you want lambda to, if you fix alpha, then lambda will not be fixed. If you fix lambda, then you will get some alpha. Now you want the values of lambda. Which lambda will work? It means lambda is cos of 2 alpha plus sine of 2 alpha. Now trigo comes. You know that this expression, a cos x plus b sine x less than equal to square root of a square plus b squared, and negative of root a square plus b square, or put it briefly, that modulus of a cos x plus b sine x less than equal to square root of a square plus b square. And so I will get that this mod lambda less than equal to root 2, giving you minus root 2 less than equal to minus root 2 less than equal to lambda less than equal to root 2, or I can write lambda belongs to the closed interval negative root 2 to root 2, and that's my answer. So that was the first part, and IT gave a second part also. That was that for lambda equal to 1, this told you that find all solutions means general solution for lambda equal to 1. So that's easy. Once you find the solution, then lambda equal to 1, it means you want to find cos 2 alpha plus sine 2 alpha equal to 1. And I told you that in this there are two approaches. So one is that one can divide by 1 by root 2 and 1 by root 2, but then because it is 1, so I would favor the other approach that I told, that I'll write sine 2 alpha is 1 minus cos 2 alpha, that is twice sine square alpha, that will be faster, twice sine square alpha, and this is nothing but 2 sine alpha cos alpha, and so I can take twice sine alpha common. I've got cos alpha minus sine alpha is 0. That gives you in fact that sine alpha is 0 or tan alpha equal to 1, because anyway cos alpha is not 0, tan alpha is 1. I get alpha is n pi, or I get alpha is here n pi plus pi over 4, and these are my sets of answers, the general solution. So this thing is over. Let's take again a question which was using determinants in some particular way. So that was again that find the number. So find the number of distinct, they wrote distinct, so distinct real roots of the equation, and the equation one given in this form, that sin x cos x sin x cos x, and cos x and sin x equal to 0 in the interval negative pi by 4 to pi by 4. So you want to find the number of solutions in this interval. Sorry about that. Now, one is that you can of course again find the determinant, but if you remember, I have always tried to give you some results which are really important. It is worthwhile to have them in mind always. So I told you that if you see some expression like a all diagonals a and off diagonals bb, so this is bb, like that I will say, so diagonals a and off diagonals b, then this expands quite easily, as you can first figure out that a plus 2b is a factor, because if I do c1 plus c2 plus c3, a plus 2b will be formed in the first column always. So a plus 2b is a root, and if you put a equal to b, then 3 rows become identical. That means that a minus b squared, 3 rows, so 1 less. This is a factor. So this is just this one, a plus 2b into a minus b whole squared. Armed with this one, it's quite easy. So in exam, you don't have to do this work. If we just know the focus, we'll just say that, okay, it is sin x plus 2 cos x, and sin x minus cos x whole square is 0. That gives you sin x equal to cos x. That's 1. So that will give you tan x equal to 1. So that gives you tan x equal to 1. And the other gives you tan x equal to negative 2. But you know that x is minus pi by 4 to pi by 4. So tan x will lie between -1. So tan x will belong to -1 to 1. So of course this value is not possible. And so tan x is only possible. And the only value of x also is pi over 4 because you are only asking this interval. And so x equal to pi over 4 is the answer. So that was an easy one. But that was quite interesting because they mixed determinant and trigonometry. And I showed you two examples where this has been done. Next is one method and one problem. First is a baby problem, means I will use it to solve some bigger problem. The message that I give from here, this is all degrees, so I will get rid of degrees. I won't write. Now, you have to solve for theta. Now, when you see this kind of thing, then what comes to your mind is, of course, componendo dividendo, because you can't miss them. Componendo and dividendo comes to your mind. They are so placed. So now I will write this as tan of theta plus 15 upon tan of theta minus 15 is 3 over 1. This is one we have written. Now I can take complementary. So what I will do before that, I use to work this thing. Tan A over tan B is lambda. This is my background work. I told you do this work to simplify the things. So don't make it ugly here because you will have so many terms. So focus on A and B. This is theta plus 15 is A here. There may be some bigger thing. So tan A by tan B is lambda. I want to use component dividendo. It means first I'll write sine A, and this is cos A, and here sine B, and cos B is lambda over 1. If I use that, I'll get sine A cos B plus cos A sine B over sine A cos B minus cos A sine B, difference in the same order, numerator plus denominator, numerator minus denominator. So numerator plus denominator and numerator minus denominator, same order, maintain the order. So this is sine of A plus B over sine of A minus B. That equals lambda plus 1 upon lambda minus 1. So I have showed you that when you see something like tan A over tan B equal to 3 by 1, a straight away jump to sine of just sum of these two angles, sine of sum of these and sine of difference of these in the order numerator minus denominator. Order is same, n minus d. And this is of course 3 plus 1 over 3 minus 1, that you won't make any mistake. Now sine, so these things help you see the correct point rather than, suppose you had written here sine theta plus 15 and upon cos theta plus 15 and all these things, it will take up quite a space also. And moreover, your mind is bogged down by writing these things rather than working on the real thing. So it means I have written the background work, I got one important result, I'm directly incorporating it here. So I'm saying that, okay, so let's do sine of sum. So sine of sum, that is sine of, wonderful, sine of 2 theta, and sine of difference in the order Newton's denominator. So that is sine of 30. That equals 3 plus 1 over 3 minus 1. And that gives you 4 over 2. That's plane 2. And so sine of 2 theta is 2 sine 30 degree. That is 2 into 1 over 2. And that is 1. And so you got sine 2 theta is 1. A very simple and plain equation. And this answer now we get that 2 theta is 2n pi plus pi over 2. And so theta is n pi plus pi over 4. Let me remark again and recall also for your benefit, students, that we have said that sine x equal to 1. We won't use x is n pi plus minus 1 to the power pi over 2. No. We will use x equal to 2n pi plus pi over 2. I showed you in the earlier class that I take n even and odd, this form emerges. So no need of this one. I can directly write this. And if it is negative 1, this just becomes negative, corresponds negative. So this formula reduces to a simple case. So please use it. This is effective in counting solutions also. So you got theta n pi plus pi 4 general solution. Based on this, I will solve a big problem which was asked in JEE 93. It was one of the toughest problem. So you're asking that find the smallest positive value. Find the smallest positive. Ask anyone who has solved this. This will always give you goosebumps. So find the smallest positive value of x. The smallest positive value of x satisfying. So they gave one system satisfying tan of x plus 100. I'm omitting the degree. It is of course degree. is tan of x plus 50 times tan of x and times tan of x minus 50. So that is your thing. You want x in degrees. X in degrees you want least positive. Now that looks quite big because a lot of tantrums are there. Notice one, this is J93. Notice this thing, that x plus 50, x minus 50, you love them because they seem to be symmetrically placed. As human people and maths people, we love them. But x plus 100, x, they don't go really that well. But we have no choice. So we will write tan of x plus 100 over tan of x. That's only left. And I will pair up tan x plus 50 and tan x minus. Let me just rewrite it so that it is little more clear. So tan of x plus 50 times tan of x minus 50. Because these two really go together, we would love to pair them up. And then now, again, same thing. I told you in the last problem that we dealt with the form tan A over tan B. Now let me deal with the form tan A over tan B is tan C tan D. What good it does? Apply again complementary dividendo because we found that A plus B came. So this work we have done. It was sin A cos B, and this was cos A sin B, and this is not done. So we'll write it sin C sin D and cos C cos D. Mind you, if this kind of thing you do in the background, you are really evolving a very powerful technique. Your time is saved, and you are getting to the point of the problem very, very fast and accurately without making mistake. This much of the work. So sin A cos B. So I again use complementary window. Sin A cos B plus cos A sin B over sin A cos B minus cos A sin B. Difference in the order numerator minus denominator. So do the same thing on the right side. So sin C sin D plus cos C cos D over sin C sin D minus cos C cos D. Once you get expert, you can do it in your head. So sine of A plus B over sine of A minus B. Be careful on the right side. Cos A cos C plus sine A sine B is good. You get cos of C minus D. That's all right. But here it is cos C cos D minus sine C sine D, negative of that. So that is negative of cos of C plus D. So I will read it as sine of, I can still use this one, sine A plus B times cos C plus D and plus sine of A minus B times cos of C minus D equal to 0. So we learned this thing, that if we have given tan A over tan B is tan C tan D, then if you play along, then it is good that you reduce it to this form. Means see this tan A, think this sine A plus B sine C. So sum and difference. So sine of sum into cos of sum plus sine of difference into cos of difference is 0. Now here, so we have derived something and we are now ready for the final assault. So we'll say that, okay, this is AB and CD. So this is sine of sum. Okay, sine of sum. So sine of sum, and then this side also it is there. So this sine of sum means it is 2x plus 100. And then this is this side. So this is your sine of cos of this sum. So this is cos of this one, that is 2x. So you write cos of 2x. And then you can write plus now sine of difference. So sine of difference is 100. Sine of difference is 100. And then one more term will come, and that is your this one, that you can write this is cos of, this is again, look at here, cos of difference. So cos of difference in the order you have taken this one. So cos of difference again 100. So cos 100 is 0. So you got sine 2x plus 100. This is 0. Multiply by 2 throughout. So 2 sine 2x plus 100 cos 2x plus 2 sine cos 100 is sine of 200 is 0. 2 sine A cos B. Change the product to sum. 2 sine A cos B is sine of A plus B. So sine of 4x plus 100 and plus sine of A minus B. So sine of 100. And then this is your nothing but plus sine 200 equal to 0. I can again do this way. Sine of 4x plus 100 plus sine C plus sine D. 2 sine C plus D over 2 that is sine 150, and sine and cos c minus d by 2. So cos c minus d by 2, that is your cos of 50. So you got cos 50 equal to 0. So sine of 4x plus 100, 2 sine 150, that is 2 into negative 1 over 2, and times cos of 50 equal to 0. Now this is plus of half. So you're getting sine of 4x plus 100, that is negative of cos of 50. So I can write this number, negative of cos 50, as negative of first sine 40, and then I can write sine of negative 40. I have taken all inside. So you got sine A is sine B. So 4x plus 100 sine theta is sine alpha is n pi plus, so 180 degree minus 1 to the power n and times 40. This is in degree, so write degree. Here it is pi. So now 4x equal to, this is n pi plus minus 1 to the power n, and then 40 degree and minus 100. Now what I can do, I can take n odd and even. So n even, first n even. So n even will give you 4x equal to, this is 2m pi n even. So that's still, this is minus 40, it was minus 40. So you will get minus 40 and minus 100. So it is 2m pi minus 140, that is 4x. So x is your, we can get 2m pi minus 100, 4x only will leave. And other case, when n is odd, you will get 4x equal to 2m plus 1 pi, and it is again odd. So if you do this, you will get ultimately negative of 60. Now you want least solution. So of course, for least solution, if you put x equal to 0 here in this one, you will get 4x equal to 180 minus 60, that is 120. And so x you will get at 30 degree. So that is your 30. The solution that you get from here, that is larger than this. So 30 degree is the final answer, because least positive solution, that is least positive solution. Okay, next, let's move to next one. Now find all x that belong to negative pi to pi such that 8 to the power 1 plus modulus of cos x plus cos square x plus modulus of cos cube x, and this to infinity, that is 4 to the power q. So we'll write like this, that we notice that this is a GP, this is a GP, and I can, because cos square x is mod of cos square x is mod cos x whole square. So I can write this as 8 to the power 1 plus modulus cos x plus modulus cos x whole square modulus cos x whole cube to infinity is 4 cube is 8 squared. So 8 squared. So you have 1 plus t square to infinity is 2, where t equal to mod of cos x. Now, if something is infinity, then you know that this equals 1 upon 1 minus t, provided mod of t less than 1. So it means common ratio mod must be less than 1. Now this is t is mod x, that is mod is this only, because cos x is from minus pi to pi. See, it's minus pi to pi, minus pi cannot be, so I will write it open. So I'll write x element of minus pi to pi open. Now if it is open, then t is not 1, and so this is all right. So it makes sense. I can write 1 minus mod cos x equal to 2, that is 1 minus mod cos x is 1 over 2. So mod cos x is 1 over 2, that is your cos x is 1 by 2 and negative 1 over 2. If you take this one, you will get x equal to 2n pi plus minus pi over 3, and this will get you x equal to 2n pi plus minus 2 pi over 3. So if you write here, from here you will get x equal to plus minus pi by 3. From here you get x equal to plus minus 2 pi by 3 in the interval minus pi to pi. Anyway, minus pi not defined, so you will get like this. And so you get four solutions. You get four solution in this interval. Okay, let's do one inequality best thing. So you want to find the set of all x that belong to 0 pi. So that belong to 0 pi, close I can write, such that 2 sine square x minus 3 sine x plus 1 greater than or equal to 0. Now, for this, first we will separate it. So it is quadratic in sine x. Let sine x equal to t. You will get 2t square minus 3t plus 1 greater than or equal to 0. I can factorize to t equal to 1 is a root. So 2t square minus 2t minus t plus 1 greater than or equal to 0. It is 2t, t minus 1, negative 1, t minus 1 equal to 0. So you will get 2t minus 1 times t minus 1 greater than or equal to 0. So that will give you that this is 1 over 2 and 1. So you will find that it is this way or this way. So t less than equal to 1 over 2 or t greater than equal to 1. But t equal to sine x, which is belong to minus 1 to 1. And so this implies t equal to 1. And here, all right. So you get sine x less than equal to 1 over 2 and sine x equal to 1. Now sine x less than equal to 1, to solve it, consider trigocircle. This is this. This angle is pi by 6. This is 5 pi over 6. At this value is 1 by 2. I have boxed it. At this also value is 1 by 2. Here value is 1 at pi by 2. So you find that if you want less than equal to 1, then you want from 0 to 2 pi. You want from 0 to pi. So this is 0 and pi. So this solution will be, you will come here and you will come here. So it is 0 to pi over 6. So 0 to pi over 6, that is closed, because you will get this one. And union, you will get 5 by 6 to pi, that is 1. And sine x equal to 1, that is just one number in the interval x is pi over 2. So the whole solution is written like this, that your set of solution is 0 to pi over 6, union 5 pi by 6 to pi, and union this number pi over 2. So that is your answer. So this answer we found for set of all solution. Next, I take up a very challenging problem, and this problem is just that there are two methods. So I'll write sine cos to the power 4x plus sine to the power 4x is 2 cos 2x plus pi over 6 cos of 2x minus pi over 6. Now, some remarks about it. The right side looks quite promising. So what I do in that right side, I will first of all change. So I can write this as cos to the power 4x and plus sine 4x. I can write as 1 minus cos square x whole square, 2 cos a cos b. So 2 cos a cos b is cos of a plus b, so cos of 4x, and then cos of pi over 3, and so you are getting half plus cos of 4x. Now I know that cos 4x I can write in terms of cos x. So looks like that equation will be a polynomial in t cos x. Now cos 4x, let me expand cos 4x. So cos 4x is 2 cos 2x. Cos 4x is rather this one. It is, first I'll write 2 cos square 2x minus 1 and 2 times cos square tx. So 2 cos x, so 2 cos square x minus 1 whole square minus 1, that is 2 times, that is 4 cos to the power 4x minus 4 cos square x and plus 1, and this is minus 1. This minus 1 is outside. This minus 1 is, so let me recall it, and this negative 1 is outside. So that is this, and negative 1 is outside. So that is plus 1 and negative 1. So I am getting 8 to the power cos 4x minus 8 cos square x plus 1. So you got this one as cos 4x. So that is half plus 8 cos to the power 4x minus 8 cos square x plus 1. Let me take cos square x equal to t. So left side becomes t square plus 1 minus t whole square is half plus 8t square minus 8t plus 1. Let me simplify a bit. So t square plus 1 minus 2t plus t square is half plus 8t square minus 8t plus 1, which becomes now 6t squared. I can calculate the term 6t squared minus 60 and plus 1 by 2 equal to 0. I can multiply by 2, 12t squared minus 12t plus 1 equal to 0. Now if that is the case, then I can solve for t as 12 plus minus root b squared minus 4ac, that is 48, and over 2 times 12. That 12 plus minus, that gives you 96 over 24. So 12 plus minus, this is 4 root 6 upon 24. And if I take 4 out, I'll get 3 plus minus square root of 6 over 6. So I have got one is 3 minus root 6 over 6 and 3 plus root 6 over 6. Remember, t was cos square x. T was cos square x, so t belonged to 0, 1. I find that both number 3 minus root 6 by 6 less than 1, and even 3 plus root 6 by 6, that also. So these both numbers are less than 1. So both can be a solution. So now I write here that cos square x, you will get cos square x as 3 minus root 6 by 6. So cos x you will get as plus root of 3 minus root 6 by 6 and negative of 3 minus root 6 by 6. And similarly, from this one I will get cos of x equal to plus 3 plus root 6 over 6 and cos x equal to negative root of 3 plus root 6 by 6. So we'll get those both, all solution, and we can find solutions and we can calculate this much longer. The second solution, so the point I want to make is in second solution what you do, instead of cos square x, pass to cos 4x. Cos 4x means go to the double of the argument, or multiple argument rather than a squared. So this is a square or fourth power. Go to, in fact, argument double or whatever, make the argument double. So what I will do that, now look at here, I will just copy from here cos 4x. So the equation was cos to the power 4x plus sine to the power 4x is, it was, again let me check, it was 2 cos 2x plus pi over 6 and cos of 2x minus pi over 6. This all right, I will write as half plus cos 4x as early. Now I will change this also to, I will not change now cos 4x, now change this one. So write cos 4x plus sine 4x. This number I will write as, again, cos square x plus sine square x whole square minus 2 cos square x sine square x. That is 1 minus 2 sine square x cos square x. Look at this one, that I can write as 1 by 2 and 4 sine square x cos square x. So I can write 1 minus half sine squared 2x. And now this I will again write as, because 2 sine squared theta is 1 minus cos theta. So it is better that you write 1 minus half, and this is 1 minus cos 4x over 2. So ultimately 1 minus 1 by 4, 1 minus cos 4x. See how careful it was. So cos 4x retain, this retain, express this, express this in terms of, express in terms of this. Earlier we did just the opposite. We did just the opposite. You can check. We retained this one, and then we get this one. Now this becomes 3 over 4 and plus 1 by 4 cos 4x. Now our equation becomes that this is 3 by 4 plus 1 by 4 cos 4x, that equals half plus cos 4x. Now this becomes that we can check our answer. So 3 by 4 minus 1 over 2 is 1 minus 1 by 4 cos 4x. We will get 3 by 4 cos 4x is 1 over 4. So we are getting cos 4x is 1 over 3. Now if this we are getting, it is easy to get, because now we are saying that let this be cos of alpha, that is alpha is cos inverse of 1 by 3 something. So we are writing 4x equal to 2n pi plus minus alpha, that is x is n pi by 2 plus minus, that alpha is there. So I'll get 1 by 4 times alpha, which I can write as x equal to n pi by 2 and plus minus 1 over 4 cos inverse of 1 by 3. Look at the simple form. This form is quite simple compared to previous method. And so we are saying that whenever you have to do such kind of thing, look at here we got such ugly numbers. This, of course, they can be matched. We can get cos 4x, but the point is that here you are getting it much simpler way, and so this method is to be suggested and this method is to be worked forward. So that we can do like this. Let's take one more example which tells the same thing, that we have got sine 4x plus 3 sine 2x equal to tan x. Now again I can write, so sine 4x is 2 sine 2x cos 2x. So I can write 4 sine x cos x and 2 cos square x minus 1. If you do that sine 4x, then you will get here sine x into 8 cos cube x minus 4 cos x plus 6 sine x cos x is sine x by cos x. I can multiply throughout. I will get sine x into 8 cos cube x minus this one. So I can write 8 cos 4x minus 4 cos square x plus 6 sine x cos square x is sine x. This will give rise to sine x, and I can bring this is 8 cos 4x, and this is plus 2 cos square x minus 1 equal to 0. So that's plain. So I get sine x equal to 0, and I can write 8t square plus 2t minus 1 is 0, where t is cos square x. Now in this one you will get here that t equal to 8t, factorize 8t square and 4t. So I can write plus 4t minus 2t minus 1 equal to 0. I get 4t times 2t plus 1 minus 1, 2t plus 1 is 0. So 4t minus 1, 2t plus 1 is 0. But cos square x belong to 0 to 1. So this does not give any answer. T is 1 by 4. So I got cos square x equal to 1 by 4. I can write 2 cos square x is 1 by 2. And 2 cos squared x I can write as 1 plus cos 2x is 1 over 2. So cos 2x is minus 1 over 2 that we get. And so we can write that 2x is 2n pi plus minus 2 pi over 3. So x is n pi plus minus pi by 3. And the other solution was given by sin x is 0. So I can get x equal to n pi. So our solution is x equal to n pi and x equal to n pi plus minus pi over 3. And this will be our final solution. If you want, you can also count number of solutions 0 to 2 pi. And you can also do this problem, try it yourself by changing or using transformation formula. So that's all for now. I'll stop saving now. So let me stop saving in. Okay, so that's all for now.